the abstract, the goal of this experiment is used to study the flow rate measurement with a comparison of pressure drop by utilizing three basic types of flow measurement technique, which is rotameter, ventrimeter, and orifimeter, and to investigate the loss coefficient of fluid through the 90-degree elbow. And this apparatus is used along with the medium water. A constant volume of 10 liter and the time taken of the water to reach until 10 liter were used to determine the actual value of the flow rate of the water of each experiment. The value of the flow rate will be compared to the value obtained from the graph. At the end of this experiment is showed that the ventrimeter is more accurate than the orifimeter and the rotameter. And the value of ventrimeter is close to the actual value. That's all.
Using a flow measuring instrument, flow meter measure the amount of fluid that flows through any pipe, channel, or space. Liquid, gases, and vapors are examples of fluids that are measured. In order to illustrate the flow measurement comparison utilizing a venturi device, orifice device, and a rotameter, we employed the Soltec flow meter measurement apparatus, which is model FM101, and the pressure drop based the flow meter in this experiment. A differential pressure sensor can measure this pressure decrease and is directly proportional to the amount of fluid passing through the meter. Nevertheless, the flow comparison may also be used to evaluate how well the hydraulic bench flow measurement work using the volumetric or gravimetric method. Since water is an incompressible fluid and this will be the subject of this experiment, a volumetric approach will be employed. So the objective for this experiment are to obtain the flow rate measurement by using the three basic types of flow rate measurement, which is root meter, ventrimeter, and orifice meter. So the objective is to investigate the loss coefficient of fluid through the 90-degree elbow. A suitable differential pressure gauge and a venturi tube compose the ventrimeter. As seen in the picture below, the venturi tube consists of a throat, a converging portion, and a diverging portion. The converging section's job is to make the fluid move faster and release more static pressure. As a result, a pressure differential between the inlet and the throat develops, and this pressure differential is connected to the discharge rate. The diverging cone transforms the velocity head into pressure head and returns the stream to the entrance area. So by assuming incompressible flow and no frictional loss from the no-D equation, so P1 over rho G plus V1 square over 2G plus Z1 equal to P2 over rho G plus V2 square over 2G plus Z2. By using of the continuity equation from Q equal to A1 V1 equal to A2 V2, so equation 1 becomes P1 over P2 over rho G plus Z1 minus Z2 equal to V2 squared over 2G in a bracket of 1 minus A squared A2 over A1 a bracket and the power of 2. So, however, in the case of the real fluid flow, the flow rate will be expected to be less than that given by equation 2 because of frictional effects and consequent head loss between the inlet and the throat. In metering practice, this is non-ideality is accounted by insertion of an experimentally determined coefficient CD term as the coefficient of discharge with Z1 equal to Z2. So equation 3 will become actual Q equal to CD multiplied by AD multiplied by 1 minus A2 over A1 in the bracket of square of 2 and in the bracket of negative 1 over 2 in the bracket 2G in the bracket P1 minus P2 over rho G in the bracket and the power of 1 over 2. The orifice for use as a metering device in a pipeline consists of a concentric square-edged circular hole in a thin plate, which is clamped between the flanges of the pipe as shown in the figure below. Figure 3, which is orifice meter pressure connection for attaching split pressure gauge are made at a hole in the pipe walls on both sides of the orifice plate. The downstream pressure tap is placed at a minimum pressure position, which is assumed to be at the vena contracta. The center of the inlet pressure tap is located between 1/2 and 2 pipe diameters from the upstream side of the orifice plate. Usually a distance of 1 pipe diameter is employed. So equation below for the ventrimeter can also be applied to the orifice meter, where actual Q equal to CD multiplied by A2 in the bracket of 1 minus A2 over A1, the power of 2, and then bracket, and then the power negative 1 over 2, and then multiplied by 2G in the bracket of P1 minus P2 over 2G over rho G in bracket and the power of negative 1 over. Total head loss delta H can be calculated by the equation delta H equal to delta H plus V squared 1 over 2G plus V squared over 2G, and then K can be calculated by delta H over V 2G over 2G. And the loss coefficient K depends on the ratio of the band radius R to the pipe interior diameter of D, which is D, and the rising ratios result in the decreasing K values, and vice versa, which is H equal to K multiplied by V squared over 2G, which is where K is the coefficient of losses, V equal to velocity of flow, and then G is the gravity, which is constant 9.81 meter per second. Okay. Square.
I would like to introduce the flow meter measurement. Okay, starting up we got control valve. Control valve will control the water flow from the pump tank. After the water will flow in up here and go through the venturi and fill up the manometer. And after you fill up the manometer, we go to the orifice. The purpose of orifice is to reduce the pressure, because if the pressure is too high, the 90-degree elbow will go burst. So that's the purpose of orifice, to reduce the pressure. And after the water go through the 90-degree elbow, it will go to the rod meter. The rod meter function is to calculate or to show the volumetric flow rate, and after water flow from the rod meter, it will go to the discharge hose, and the discharge hose is controlled by the discharge valve, and we will fill up this tank. It's called the volumetric tank, and this indicator will show the liter, how many liter that fill up the volumetric.
Starting up operator, first we must switch on the pump switch and let the control valve fully close. The next one is the discharge valve must be fully open, and then we must ensure that the discharge hose is perfectly located at the volumetric tank, and then we must let the bench valve open to let the airflow into the sump tank. After that, we just open the control valve slowly to check if the water flow through all the apparatus or not. As you can see, the discharge valve is fully open just now. The water flow through the volumetric tank and get back into the sump tank. After that, we must close the bench valve and proceed.
So we go on to the orifice. We go on to the 9 demonstration table 3. What we can see here is the differential piezometer head, which is the blue yellow. You can see it slightly increases, but the velocity head, which is the orange color, you can see it increased drastically, which from about 1 to 9, about 9 calculation that that I used to calculate the flow calculated using Bernoulli's equation. So this is the calculation. So you can see here is I'm using the Q equals to CD times AT times in the bracket 1 minus bracket um, A at min RA minus A in the bracket time square close bracket power of negative 1 over 2 open bracket 2g gravity in bracket h a minus h1 minus h2 close bracket power of 1 over 2. So this is the equation that I'm using. So for to clear out the equation, you can see at the theory of this experiment. You can see the variety of calculation formula. So I'm using this calculation formula to calculate the flow through Bernoulli's equation. So you can see for that CD, A, and G you can get from the theory section. So this is the calculations for the venturimeter flow rates and orifice meter flow rates.
As for the discussion, the experiment successfully obtained the flow rate measurement with a comparison of pressure drop using three basic types of flow measurement techniques, which is the rotameter, venturimeter, and orifice meter. We used to collect the data needed for this experiment. It was using the rotameter. It is possible to adjust the venturi and orifice meter setting to enhance the flow rates. 3 liter water constant volume was also used to calculate the actual flow rates for each experiment. The various rotameter flow rates cause variation in manometer readings, which A, B, C, D, E, F, G, H, I, and J. The pressure drops across the flow meter at different places are represented by this value. According to the data we obtained, the pressure drop usually correlates with the flow rates. The height, which the difference in levels for every manometer was not. After acquiring the manometer readings, the value for the venturi tube and orifice plate were computed using Bernoulli's equation in liter per minute. The result of the computation were recorded. The flow rate of the venturi tube was determined using the reading of manometer A, B, C, D, E, and F, while the flow rate of the orifice plate was determined using the reading of manometer G and H. After that, the manometer I and J are used to calculate the 90-degree elbows. The manometer measurement shows a steady trend when we increase the rotameter flow rates from 5 liters per minute to 20 liters per minute. For example, at point A and B, we can observe that the manometer reading increase in parallel with the flow rates. For the first experiment at point A, the readings range from 270 to 344 millimeter, whereas at point B, they range from 270 to 329 millimeter. This will indicates that as the flow rate increases, the pressure drop across the flow meter at this location become more noticeable. The trend where the manometer readings grow with increasing flow rates also seen at point C, D, E, F, and G. This demonstrates that the pressure drop and flow rates are correlate. The manometer readings at point A and B typically increases as the rotameter flow rate does. This suggests that increase the greater pressure drops the outcome of the flow rates. At other points, which is C, D, E, F, and G, the same pattern is seen, indicating the variation in pressure throughout the system. The relationship between flow rates and manometer readings in our experiment is increasing with fundamental ideas in fluid dynamics. Specifically, the notion of pressure drop in a fluid system. The time taken for the water to reach a volume of 3 liter decreases as the rotameter flow rate increase. This is consistent with the higher flow rates allowing for a faster filling of the volume. The inverse relationship between time and flow rate is typical in fluid dynamics. Time taken for the first experiment when the rotameter is 5 liter per minute is 52.9 seconds. For the 10 liter per minute is 31.26 second. For 15 liters per minute is about 18.78 second. And the last one is 20 liter per minute is 13.62 second. Meanwhile, for the second experiment for 5 liter per minute, it took about 52.9 seconds. The 10 liter per minute took around 31.26 seconds, and the 15 liter per minute took time about 18.78 seconds, and the last one is 20 liter per minute, which took about 13.62 seconds on the rotameter. Based on graph of differential piezometer head in millimeter versus velocity head in millimeters, we know that the slope of graph determine the loss coefficient, which is K equal to delta H over V square over 2G. Piezometer versus velocity head graph is crucial example in fluid mechanics and hydraulics. Due to the 90-degree elbows, it helps to illuminate how pressure is distributed in fluid that is moving and clarifies the energy related issues with fluid flows for manometers I and J. The total energy per unit weight of fluid at a specific position in a flowing fluid is represented by piezometric head, which is occasionally written as Z. It is made up by the three components. The elevation head, which is potential energy resulting from head above at reference point. The velocity head, which is the fluid kinetic energy, and pressure head, which is energy resulting from the fluid pressure. One essential tool for analyzing fluid flow comprehending the distribution of energy in a fluid system is the piezometric head. The piezometric head, velocity head sometimes represent the letter V. Is then accounts for the fluid kinetic energy is proportionate to the fluid velocity squared. The velocity head is significant because it shows the percentage of total energy at point that may be attributed to fluid motion. As fluid velocity increases, the velocity head rises, indicating the piezometric head is receiving more kinetic energy. In a fluid flow system, the connection between these two parameters at various places or along a streamline that are typically displayed on the graph of the piezometer versus velocity head. The y-axis represent the piezometric head and the x-axis represented the velocity head. The graph usually shows a linear relationship between two parameters, especially for constant incompressible flow along the streamline. This linear relationship is directly related to Bernoulli equation, which state the total elevation head, pressure head, and velocity head along the streamline that remain constant as long there are no energy losses, such as those brought on by friction or turbulence. This will conclude that Q rotameter more than Q orifice, and Q orifice are more than Q actual. Lastly, the Q actual are more than Q venture. Conversely, orifice meter are the smallest and more simplistic in terms of construction. The sudden shift in flow areas in the orifice meter creates a light swirl, and the vena contracta narrows as flow velocity increases. The size of the vena contracta increases the pressure differential, which result in a significant heat loss and increase in energy loss. Orifice meter typically have the highest minor loss coefficient, while venturimeter have the lowest. We were able to observe the fluid flow via the 90 degrees elbow in the second experiment. The pipe causes the separation and mixing, adding to loss and interfering with the fluid smooth flow. To determine and moderate losses, theoretical analysis is often not a practical method. Thus, an experiment is conducted to find the tiny losses, which are often described in terms of resistance and loss coefficient.
Knowing that flow rate is the amount of gas or liquid moving through a pipe per unit time, it is usually represent the symbol of Q. The SI unit is meter cube per second. Flow rate was measured with an orifice meter, ventrimeter, and a rotameter in this experiment. This measuring technique, operating, and characteristic will be determined by comparing the calculated pressure drop that is related to the velocity of the fluid in the pipe using Bernoulli and continuity equation. According to the data, the high pressure drop for orifice meter is unrecovered. This is because the flow rate is increased at the opening of the orifice plate and not much energy is lost, but as it flow through and slow down, much of the excess energy is lost. The energy loss were significantly higher for rotameter compared to venturi and orifice meter. The large drop in pressure caused by friction causes the high energy loss. The value obtained for ventrimeter was closer to the actual flow rate due to the lower pressure drop caused by the streamline shape, which almost eliminate the boundary layer separation, and thus from that is assumed it is negligible. Although there may be some pressure loss in the converging part of the ventrimeter, in proper design ventrimeter, some percentage of pressure loss is attained back in the diverging part of the meter. This meter is useful for higher pressure and energy recovery. In conclusion, the ventrimeter was more accurate than the orifice and the rotameter. Based on the result of this experiment, there are many approaches to improve the experiment and to obtain the best result. We must ensure that there are no bubbles to increase accuracy and avoid reading error. By using a pen or a screwdriver, you can depress the stator valve that located on the upper right side of the manometer board. Depress the stator valve slightly to remove any trapped air or liquid. Allow enough time for all the bubbles to escape from the fluid. We also need to monitor the water level on the manometer board. If the water level is too high, which is above the visible position in the manometer board, we must use the stator to lower it back down. Nextly, we should take the manometer reading at eye level, which is perpendicular to our eye, to avoid parallax error. We must avoid parallax error if we want to obtain reliable data and outcomes. The experiment must run 3 times to get average error. This will reduce the amount of theoretical outcome divide. To get a better result, the experiment go to been conducted at least twice. Finally, before starting any experiment, make sure you understand the device and protocol completely. We need to go over the lab manual again and again to understand this experiment. For us to successfully finish the experiment and to understand the unit in its process.